Welcome to this video where I'm going to explain phase matching, self-phase modulation, and third-harmonic generation. By the end of this video, you should hopefully have an intuitive picture of why this condition needs to be satisfied if you want to take light at one frequency and generate light at 3 times that frequency using the chi3 nonlinearity. So let's get started. In a previous video, I explained how to derive the following equation which relates spatial changes in the E field to temporal changes in the E field, as well as to the response of a material that the E field might be propagating through. In the very simple case where p is equal to 0 always, then this equation will simply describe the propagation of EM waves inside of a vacuum. In the slightly less simple case where p is linearly proportional to the applied E field, then we get an equation for the propagation of EM waves inside of a medium. But what happens if p is not directly linearly proportional to E? What if it also depends on the cube of the E field via a so-called chi3 nonlinearity? That's essentially what we're going to discuss today. First of all, we should try to understand why the gradient of the divergence of the E field can be neglected in most glass waveguides. Essentially, we can express the E field in the following way as a difference between a displacement field d and a polarization field p. And if you want to understand exactly what these fields mean, check out the video I've linked up here. If we plug this expression for E into the expression for the gradient of the divergence, we get this term right here. And if we then note that the divergence of the D field is dependent on the local density of free charges, while the divergence of the P field is related to the local density of bound charges, then we can note that if we're inside of a glass waveguide, there's not going to be any free charges, so we can cancel out this term right here, leaving the divergence, or rather the gradient of the divergence of the E field, to be expressed in the following way that only depends on P. So the next step is to note that P must be some kind of function of the E field, and at this point we don't know exactly what that function is, but we're going to assume that it can be Taylor approximated. So essentially, we're going to assume that this first term here in the approximation, which we call P linear or PL, is very large compared to all the other terms, which we can collectively refer to as P nonlinear. So this dominant term here, we can write this as a convolution between a tensor chi and the E field E right here. So let's just go into that in a bit more detail. So first of all, chi1 should in general be a tensor, because it's possible that if you launch an E field into the medium along one direction, it could actually give rise to a P field in some direction that's not parallel to the initial E field. And that could be the case if the crystal you're sending the light into is not completely homogeneous. For example, if it has a different refractive index along the x and y directions and you launch the E field sort of an angle. But if we make the assumption that the medium is completely homogeneous and uniform, we can assume the chi1 is just a scalar. The convolution integral here is present because if you apply an E field to a material, then all of the dipoles that are present inside, which give rise to P, don't necessarily respond instantly. They might actually take a while to adjust and align themselves with the applied E field. So the convolution simply taking this effect into account that the response of the material is not completely instantaneous. However, one trick we can do is to note that a convolution in the time domain is equivalent to multiplication in the frequency domain. So that makes this expression a little bit easier, because if we take the Fourier transform on both sides, we can simply write this as a multiplication of the chi1 tensor, now the frequency domain, onto E. And again, of course, we're going to assume that this is not a tensor, but just a scalar. So again, much nicer than what we have up here. If we then plug this into the expression for the gradient of the divergence of the E field, again, now we're looking in frequency space, we get this expression over here, which we can simplify a little bit. So first of all, we can cancel out the epsilon naughts and then add this to the left-hand side, showing that we get two terms which added together should give us 0. Next, we're going to neglect the spatial dependence of chi1, and essentially we do this because when we're inside of a waveguide, then the refractive index is related to the value of chi1, and in most glasses and most waveguides, this is not going to have a very strong spatial dependence, so we can just neglect this spatial dependence, which allows us to move chi1 outside of this gradient divergence operator in the following way. Then we can note that we can factor out these gradient divergence terms in this way here. That gives us two factors, which when multiplied together should give us approximately 0. So if that's the case, then either one of these must be very close to 0. Now if we look at the first one, we can see that if this one is 0, then it requires chi1 to be equal to -1. And that'd be very strange, because it basically means that if you have a neutral atom inside of this crystal structure, and you apply a positive E field along the upward z direction, then basically that should cause all of the positive charges to shift downwards towards the source charge down here. And that's very strange, because in this case, it's almost as if like charges attract and opposite charges repel, which is opposite of how electric charges usually behave. So maybe there are some materials that behave like this, but most glasses you're going to encounter certainly don't do this. So the only other option is that the other factor here must be 0, and that indeed is correct. which is very nice because that allows us to rewrite the master equation in the following way by dropping this gradient divergent term over here to the left. So next we can split up the polarization into the linear part and the nonlinear part like so. And again, just to reiterate, now the equation is describing how the spatial change in the E field relates to the response of the vacuum to the applied E field, as well as to the linear response of the medium to the E field, and then finally the nonlinear response of the medium to the E field. So let's take a closer look at this nonlinear contribution here. First of all, we can neglect the chi2 behavior for symmetry reasons. Again, we're assuming that the material we're propagating through is homogeneous and uniform, and essentially this implies that the chi2 part has to be 0. And again, the reason's a little bit complicated, but I've linked a video down in the description that should hopefully clear this up. Also, we notice that there is a tensor product now between this chi3 tensor and then basically 3 electric fields at different times in the past, and then also convolution over all these different times here. So if you think this is very complicated, I don't blame you, but fortunately we can make a few simplifying assumptions to make this a bit easier. First of all, we can assume that the response of chi3 to the applied E field is instantaneous, because in that case we can simply neglect all of these convolutions. Furthermore, we can assume that chi3 is just a scalar, and in that case we can write the nonlinear polarization as simply chi3 multiplied onto the cube of the E field directly. Then we can plug this into the master equation, giving us this result right here. So essentially our goal now is to specify some initial value of the electric field, and then see how it evolves as we propagate through the medium. Before we get into all the math details, I want to just give an intuitive picture of what this master equation is really saying. So if we have this expression right here without the nonlinear contribution, the equation would simply describe how a regular wave propagates through a medium with some refractive index, which you may have seen before in classes and whatnot. However, if we add on this nonlinear term right here, then there's a different way to think about it, or at least one that I think is very convenient. I think that essentially you can view this as an ordinary wave propagating through a medium, along with a very large number of very small antennae that are present all the way throughout, which emit in a way that's proportional to E, the local E field cubed. So in other words, if we have this wave propagating, every single one of these little antennas are basically checking what's the local cube of the E field, and then it's going to emit some additional field in a way that depends on the cube of the E field. And then whatever field that comes out on the other end here is just going to be a combination of the wave that's already present, plus all of these contributions that are coming out from all the little antennas. I know this is a bit artificial, because obviously these antennas are like actually part of the medium and are being sort of excited by the E field that's already present, but it's kind of convenient to think about this as being the sort of regular wave that's propagating through the medium normally, and then you have this additional sort of artificial contribution from all these antennas inside. Hope that makes sense. It's going to be quite a useful picture in the following slides we're going to see, so just keep that in mind. Anyway, so how do we mathematically model the evolution of the E field? We could of course use the total E field, but that's actually kind of tricky to model. So instead we're going to split this E field into a very large number of discrete frequency components, and then hopefully we can model the evolution of each of those separately, and then just add them up in the end in order to get the evolution of the total E field. So essentially we're going to write the total E field as an infinite sum of individual frequency components like so, and of course we can express that using the complex formalism. Essentially what we're doing here is saying that if we have some kind of E field signal, for example a pulse with some kind of, let's say, a frequency spectrum, then instead of modeling that as being completely continuous, we're going to write that as an infinite sum of very, very small frequency components like so, where we can basically tune the resolution by adjusting this omega parameter. And in this equation here, when I write beta sub m, I mean the spatial frequency evaluated at a certain temporal frequency like so. So another small assumption we can make to simplify things is to say that the E field is always proportional or polarized along the x direction. So in that case, we can turn this equation into a scalar one instead of a vectorial one, which makes things a little bit simpler. Now again, this prevents us from actually modeling a lot of sort of polarization dynamics that actually do take place. But again, for now, we're just trying to get an intuitive understanding of this master equation, how to go about solving it. Then we can always add some more complications later. Alright, so now we're going to introduce what I like to call the one-wave mixing approximation. Essentially, we're going to assume that the cube of the E field is just given by the cube of the omega 1 component, like so. In other words, even though we actually do have other frequency components present, we're going to assume that the dominant one is simply the omega 1 term. In other words, this implies that the frequency at omega 1 can actually affect other frequencies via this chi3 nonlinearity, but none of those other frequencies can affect omega 1, and they can't affect each other. So all of the nonlinear behavior is sort of dominated by this omega 1 frequency term. If we then compute this cube of the E field, we basically get the following result here. And I guess technically this should not be an equals, but rather an approximation sign like so, but I think you get the point. So what is this telling us? Well, essentially it's telling us that these little antennae I mentioned earlier will partially be emitting at a frequency that's equal to 3 times omega 1, and partially at a frequency that's equal to omega 1. Alright, so another thing we can do to make things easier is to compute the Fourier transform of the master equation. And basically that replaces derivatives in time with multiplications in frequency. So if we do that, we can notice that this term is proportional to E as well as this term. So if we move this over here, we can simply turn this into the spatial frequency squared like so. And with this whole equation here, we can also take the Fourier transform of the sum expression for the E field that I've shown earlier. So if we take the Fourier transform of that sum, we can note that any complex exponential that involves time will be turned into a delta function in terms of frequency. So the E field will basically contain an E1 component and an E3 component, which each have these delta functions that are present. If you also take the Fourier transform of the cube of the E field, then we get this expression here, where once again we see these delta functions arise. Now, plugging these expressions into the master equation, we can see that it gets a little bit complicated, to say the least, with all these delta functions and different terms that are present. But one thing we can notice is that all of these terms right here all contain delta functions in omega 1, while all of these terms here contain delta functions in omega 3. That's very convenient because it allows us to basically split this very large equation up into two separate ones. We can simply select one of the omega values in turn, and that gives us this equation here separated from this other one, where you can see this one only depends on the omega 1 frequency, and this one down here only depends on the omega 3 frequency all the way throughout. Okay, so now let's try and focus on omega 1 first. First of all, we're just going to drop the complex conjugate for now, because we can always get it back later if we correctly solve for this complex number E1. It's just a matter of conjugating the result in order to get E1 star, from which we can then recover the actual E field. Okay, so how do we actually solve this equation here? Well, first of all, we can ignore the x and y dependence of the field. We're just going to assume that the only change that's sort of interesting or significant is the change as we move throughout the medium. That allows us to replace this double gradient with the double derivative in Z. Okay, so with that we get this expression here for the double gradient of E1 multiplied onto the complex exponential here. So furthermore, we can also assume that any changes that are happening as we propagate through the medium are quite slow compared to the rate at which the field sort of naturally oscillates. In other words, if the field sort of grows as we move forward, then the overall change in the field is going to be quite slow compared to the rate at which it sort of oscillates up and down naturally. I hope that makes sense. But the basic point is that this allows us to cancel out the second derivative in E, giving us an equation that only depends on the first derivative of the E field. Again, makes things a little bit simpler. If we then simplify a bit further by multiplying out that parenthesis we saw earlier, we can see that these two terms will actually cancel each other out, giving us this expression here for the gradient of E1, which then reduces to this expression here. If we then go through the same steps for omega 3, then we can see that we get the same cancellation as before, and the following expression here for the derivative of E3. So now we have a set of coupled differential equations which explain how the E1 and E3 field components will evolve as we propagate throughout the medium. Now, in general, we could use some kind of numerical solver to model how these two evolve, but it turns out that in this very simplified case, it's actually possible to analyze this analytically. So one thing we can note is that the first equation here is independent of E3, and the other one is dependent on E1. That kind of goes back to the one-wave mixing approximation I showed earlier, where we assumed that the omega 1 term is sort of dominant. So that kind of explains why this term here is only being affected by E1 itself, while this one is also being affected by E1. But you can see this term here is not being affected by this one down here at all. Okay, so how do we actually solve this analytically? Well, the first one's actually fairly easy, because it basically says that the change in the complex number E1 is basically a 90-degree rotation of that number by an amount that happens to be proportional to the magnitude of E1. So again, if you think about this in the complex plane, it's basically saying that if you have the complex number E1, then if you rotate that 90 degrees, then that gives you the orientation and magnitude of the gradient. And so if you keep taking very, very small steps that are always sort of orthogonal like so, you can see this complex number is going to rotate around like so, but not actually change in magnitude. So with that in mind, we can basically integrate this and find the following expression for the evolution of E1 as we propagate forward. As you can see, it's equal to the whatever value it has in the beginning, multiplied by this complex exponential, which depends both on the absolute square of E1 as well as on Z. And remember, whenever you see the absolute square of an E field, you should think about this as being proportional to the power of that E field. So if you plug this back into the expression for the omega 1 component in the sort of real domain, you can see that we have this complex exponential as always before, but also this extra term here that kind of behaves a little bit like a spatial frequency. In fact, if we add these two together in the following way, we can see that we end up modifying the spatial frequency of the omega-1 component in a way that's proportional to the power. So that's kind of the interesting part about the chi-3 nonlinearity. It sort of allows the light to affect itself as it propagates through the medium. And just to highlight exactly what is going on here, let's imagine that we launch a very low power wave into the medium. Well, in that case, the spatial frequency is simply going to be equal to whatever the spatial frequency normally is, even without any nonlinearity. But if we simply boost the power like so, that's going to increase the spatial frequency. Or you can think about the wave as being sort of squeezed more together, because a higher power means that you increase the refractive index of the wave, which then changes the spatial frequency in the following way. Now, the exact amount by which it changes in this diagram here is very, very exaggerated, but it's just to give you an intuitive picture of what happens as you increase the power. It's going to increase the refractive index, which then changes the spatial frequency. And this is the effect known as self-phase modulation. Okay, so what happens if we look at the omega-3 component? Well, if we substitute in the expression for E3, or rather E1 cubed, we get this contribution right here, but we can actually neglect this exponential right here, because usually the change in the refractive index due to the power of E1 is going to be quite small. Then we can simply integrate this on both sides, and if we do a little bit of clever math, we can show that this actually depends on a sinc function of this difference in spatial frequencies. And if we take the absolute square, we find that the power of the E3 component is going to depend on the sinc square of this term here, and then also the length, as well as the power that we launched in the beginning via this constant A coefficient that depends both on E1 cubed as well as on the chi-3 parameter. So this essentially is what we call third-harmonic generation, because you can see that energy at 3 times the frequency is being generated by the initial frequency that's present. You can also see that the efficiency of that process depends on this weird sinc function here. So clearly, if you increase the value of this parameter, then the amount of power you get out at omega-3 is going to drop. Now, it's always nice to observe this mathematically, but I think it's more important to understand physically why is this actually the case. What is this difference in spatial frequency actually doing in order to decrease the efficiency of that power transfer? So to understand this, I think it's helpful to assume that we have a very simplified case where we just have an omega-3 wave that's propagating through the medium. We want to use all these little antennae down here in the box in order to boost the power. So the question is, how should we arrange these in order to get maximum efficiency? And the easy answer here is just to arrange them in such a way that they're always in phase with the local wave. And again, I like to think about this in terms of constructive interference. If you're standing over here and want to observe as much wave power as possible, then you want to make sure that the wave that's propagating inside the medium and all these little emitters that are adding additional wave power are all emitting in sync with the wave at any given point, because in that case you get the maximum amount of constructive interference in the very end. So again, that's kind of obvious. But what happens if we can't just place these antennas arbitrarily and give them any arbitrary phase? What if they're sort of riding on a different wave which has a different spatial frequency? Well, in that case, you can see that the emitters that are tied to this wave are not necessarily in sync with the target wave anymore. They might actually be a bit out of sync. So in that case, we don't get maximum constructive interference over here anymore, and we might actually get a bit of destructive interference, which overall reduces the total wave power. So the way to think about this term right here is basically as the difference between the sort of the source wave that you can see right here and the target wave. If these don't have the same spatial frequency, then power doesn't get constructively transferred from one into the other. So now that we understand this term here as being a phase mismatch, we can look into its value in a bit more detail. So first of all, we can rewrite this in terms of the refractive indices and the temporal frequencies. And then if we note that, of course, omega-3 is equal to 3 omega-1, we can factor that out and note that the difference in spatial frequencies, or the phase mismatch, depends on the difference in refractive indices. So for silica, we can simply graph what this refractive index is. For example, on the red curve, we see the actual refractive index, and on the blue curve, we see the index at 3 times that frequency. For example, here at 150, we can see the index has a certain value. Then we can go up to 450 and see what value it has here, and then simply graph that over here on the blue chart. So basically, the point is that in any location where this difference here is small, we're going to have a small phase mismatch, and then a more efficient power transfer from the initial frequency into the 3 times that frequency. Another way to think about this is to ask when this expression here is equal to pi. Because if you think back to the sinc squared function, you can note that it has its first 0 at a value of pi. And sort of beyond that, you get very, very low efficiency. So in other words, we can think about this L here as being a coherence length, and then ask how that depends on the difference in spatial frequencies and in refractive indices. So graphing out this expression here, we get this curve here for the coherence length inside of silica. So what we notice is that if we, let's say we pick like 150 as our sort of test frequency, we can see that after a small distance, these two waves, both the carrier wave at omega 1 and the target wave at omega 3, are still sort of spatially in sync. But as we move further and further along, they sort of grow out of sync. And sort of beyond that, we don't really get very much power transfer from omega 1 into omega 3. Note also that for the case of silica, you can see that the scale on which we're operating here is in micrometers. In other words, if you're trying to do third-harmonic generation, silica would be quite a poor choice for achieving that, since essentially you can only really use a piece of silica that's a few micrometers long. Beyond that, it doesn't really benefit you any further. So when you're doing nonlinear optics, it's really important to sort of choose the right material and choose the right carrier frequency in order to do the generation that you're interested in. But of course, this is kind of an advantage in telecom if you think about it, because if there was a really good phase matching going on inside of the telecom wavelength range, it would mean that as soon as you're trying to launch light into a fiber, for example, then lots of the power will always escape into 3 times that frequency and sort of get lost. That would be kind of annoying. So it's kind of a trade-off that you have to keep in mind. Alright, so with all of that said, I wanted to summarize all the different approximations we've applied in this video. I just simply listed them out right here. It's maybe a bit too much for me to go through in complete detail, but it's just to show that the model we've presented so far is just an approximation. There's a lot of dynamics and a lot of interesting phenomena it's not taking into account, but it does serve as a good starting point, both for doing this kind of analysis, but also understanding this phase matching procedure. I think probably the most important simplification we've made here is the one-wave mixing approximation, like so. Because if we, let's say, add additional terms, for example, the omega 3 term, we'd be able to model not just the power transfer from omega 1 into omega 3, but also the other way around. Furthermore, if you want to model something like four-wave mixing, all you have to do is simply add more frequency terms inside of the approximation and then compute how they interact. And you're still going to have phase matching terms and whatnot that are present, but still this sort of gives you an overall approach. In some way, I think four-wave mixing is kind of maybe a bad choice of words for this phenomenon. I think really it should be called multi-wave mixing, and then you should understand that one-wave mixing, two-wave mixing, four-wave mixing, and so on are just sort of, let's say, levels of approximation to the true behavior of the light inside of the medium. But maybe I'll make a video about that at some later time. Okay, so just to summarize all the results, we've shown that this equation here can be used to model the propagation of light inside of a medium subject to a so-called chi-3 nonlinearity. We've seen that we can understand the process of phase matching by thinking about these little antennas that are riding on waves and then sort of dumping power from one frequency into another one. And that in turn explains why you must have that the refractive index at one frequency is equal to the refractive index at 3 times that frequency in order to get sort of efficient third-harmonic generation. Alright, that's all for now. Feel free to check out some of these other videos over here, and stay tuned for more. Bye bye.